Hello, and a very warm welcome to everyone joining us for today's Select Science webinar, titled From Powders to Paint Chips, Modern Microspectroscopy Draws Big Information from Tiny Samples. My name is Rory Shadbolt, and I'll be moderating today's session. I'm delighted to be joined by Dr. Michael Bradley from Thermo Fisher Scientific. Today, he will show how you can improve the speed and accuracy of your microspectroscopy results. After the presentation, we'll move on to our question and answer session. Please feel free to ask any questions for the Q&A session at any time during the webinar. You can submit your questions at the left of your screen. Just click on the purple tab. Now, there will be some live polls being sent around during this webinar, so please feel free to answer if they apply to you. And without further delay, I would like to hand over to Dr. Bradley for today's presentation, and I would like to thank him for presenting to us today.
Just said, I am Mike Bradley, the Senior Product Manager at Thermo Fisher Scientific for the FTIR spectrometers and microscopes. What I hope to do today is mostly a tutorial about the use and the operations of the FTIR microscopes. So I'm going to show you some about sample preparation. Actually, I can go to the first slide now and show you that. The first question that we wanted to answer was why? Why FTIR microscopy? And who uses it? The answer to who uses it is fairly easy, and that's anybody in an analytical lab or a quality control lab or an R&D lab. It is a very commonly used tool in all of those places, and I've been in many forensics labs all around the world looking at what they're doing with the microscopy and the examination of trace evidence, art restoration, and basic research. And why? The advantage of the FTIR microscope is its ability to do everything you do with normal microscopy and also everything you would do with spectroscopy, and you combine the two. So you're looking at identifying or locating particular materials within your sample, like in failure analysis, reverse engineering, new product development, art conservation, identification of trace evidence, as I said, in the forensics field, and any kind of microscale chemistry. So it may be as simple a question as I've got this fleck of some contaminant and I need to identify it, and it's just a tiny little piece, or it could be as complex as identifying the signature of various components in ancient paintings to identify whether or not they could be counterfeit or forgeries or the real deal. So there's a lot of uses for the FTIR microscopy, and I'm going to show you a few of those throughout the talk. As I said in the outset, there will be two parts to this. The first will be how-to, because sometimes sample prep and the choice of the different sampling techniques may be the most difficult part of the whole analysis. And then we'll look at some applications. As you look through this slide, we will see most of these in the presentation. To the far left, that is a monetary piece, and I will talk about that more later. Then you see the single fiber that we've analyzed by attenuated total reflection, the large rock at the top that we've analyzed, then the big painting that's on there. In the bottom center, that is a pharmaceutical tablet, and then to the lower right, you see one of the more exciting new types of samples. That's the analysis of a microplastic sample. So I will be going through most of those during the presentation. Now, when you're analyzing or looking at your samples by microspectroscopy, there are three ways to analyze them. The first and most common turns out to be point and shoot. And that is where you have a single sample or you have a single defect or something that you need to target and analyze. And again, shown there is the fiber. The next most common is mapping, where you look at an area of the sample and you characterize that small area. This is what I've shown here is a multi-layer film, and I will talk more to that during the presentation. And then finally, imaging, which is done when you're looking at an entire sample and you want to characterize maybe the distribution of an ingredient in it. What's shown there is a diamond, and we were analyzing the defects in the diamond. That was actually done by Raman spectroscopy. And the point there is to get an array of spectra and extract chemical information. Now, one thing I want to connect here at the beginning is that imaging and mapping are essentially the same thing. In imaging, you get an area map or an image out, and in mapping, you do it point by point. The key difference with an imaging is that you collect a large area in one pass. In mapping, you do it point by point, but in the end, you build up the same level of information in the two in general. So now let's move on and look at the three different microscopes that we'll be discussing here today. On the left is the Nicolet IN5. This is a very small manual microscope, very easy to use. In the center is our Nicolet IN10 microscope. It stands alone, doesn't need a spectrometer attached, and it can do imaging. So that's when we talk about imaging, that'll be this microscope we use for FTIR. On the right, I am very, very proud as of today to be announcing a brand new FTIR microscope that we are launching as of February 1st. This is the Nicolet RaptIR FTIR Microscope. You'll see many spectra and many visuals from this microscope as we go through, so I won't talk more about that, except to say that it has really outstanding spatial resolution, both in the infrared and the visible. So now let's move to the different collection modes. So this is the tutorial part, sample prep and sample analysis. At the outset, there are two major ways of analyzing your sample. First, there's transmission, and then there's reflectance. In transmission, the light goes completely through the sample. This is really the preferred method if you at all can use it. And the reason is you get 100% of the light through the sample, except what it absorbs. Gets the most light onto the sample of any of the techniques. However, it can be the most difficult to prepare the samples because the samples need to be really, really thin. They're mixed and pressed, cut with a microtome, flattened, but it has really good sensitivity once you get it there. In reflectance, there are three different modes. By far, the most common is attenuated total reflectance. This is where you just touch the sample. The sample must contact the crystal. You see the crystal over there to the right. That is the tip. You can see the point of the sample. And ATR has the advantage of being very simple, very fast, non-destructive, and also doesn't really require any sample preparation. The next one down is diffuse reflectance or drifts. This is where you just have like a white heterogeneous material, something like a tablet or a dosage form in a pharmaceutical setting or a powder. It can also be used on documents, such as in a forensics when you're looking at ink on paper. That is a type of drifts. And then the last one is specular reflectance. This is where the sample must be highly reflective or thin and on a mirror, and I will show a laminate where that's the case. It could also be like a thin film of a lubricant on a automotive, something like an automobile cylinder, something like that, and you're just looking at the oil, that thin film, but the cylinder is highly reflective. The advantage of this is, again, it generally doesn't require a lot of sample prep, and it's very fast to do, but the signals can be very, very weak. And if the sample's too thick, you go through it twice, in many cases, what's called infrared reflection absorption. And if you go through this, and I'll talk more to that in a minute, so I'll stop there. But the key here is that you have two main methods, transmission, reflection, and then under reflection, you have a couple of different ways to look at the sample. Now, the workflow in microscopy starts with you choosing your technique and preparing the sample. If you have a very large sample, you need to cut it down in size, or you need to, because you can't go through the whole thing if you want to do it by transmission. So you got to figure out how you're going to make the sample. Then once you've got the sample, you need to locate the target, select the sampling mode, set your experiment up on the microscope, and then collect the data finally. It turns out that collecting the data usually is about the fastest step in the analysis after you've prepped the sample and everything. And then you analyze the data, whether it's analyzing specs, looking at a large number of particles like microplastics, and that's what you see on the bottom right over there. In the slightly above that is a sample on a gold slide that I'll be discussing momentarily. And then at the top, you have a sample that's in a transmission mode analysis. That's a single fiber of a material. Then you transmit that information, meaning you prepare a report, get it to your stakeholders, and then distribute that information wherever it needs to go after you've analyzed it. So the whole workflow starts with the sample collection and preparation, all the way through to getting the report to the appropriate stakeholders in the format that they need to receive it. Now, this is kind of a broad overview of that process through the sampling portion of it. Now, if the sample can be easily extracted, I'm not going to read each one of these boxes, then you transfer it to a salt window or a diamond window or something, a compression cell, and then analyze it by transmission if you can. If you can't, then you flatten it onto a surface and run by reflection. If the sample can't be extracted, say it's a geological sample and you're looking at something deeply embedded in it, then you either have to dig it out or you have to analyze it in situ. And again, that would apply to a film on a surface or something like that. So then you use one of the reflection techniques. And again, as I said, ATR is probably one of the preferred, where you just touch the sample, do your analysis, and be on your way. And I'll show that in a moment. Now, the advantage of transmission, as I said earlier, is that it gives you the best spectral quality. It has no artifacts that you see in the reflection. In ATR, you'll see peak shifts. In infrared reflection absorption, you can have a sample that's too strongly absorbing, things like that. But in transmission, you get the best signal to noise, as I said, because you're getting 100% of the infrared energy through the sample. The cons or negatives is that the sample thickness must be just right in order to see it, and the sample needs to be IR transparent. So you can't analyze something on metal or paper by transmission. So typically in transmission, it's going to require some sort of sample preparation. To the lower right over there, you see a sample that I'm going to show you more about. That is a multi-layer film or a laminate, and sitting next to it, the larger piece you see is potassium bromide. And the reason for that is on this slide. Well, no, I'll show you that in a moment. I'm sorry. The pros of specular reflection is there's no sample prep. You basically just hit the sample with the IR beam and you collect the data that comes back. So the sample thickness in specular reflection doesn't really matter. The cons are that you get low spectral quality and you can see some very strong artifacts. If you look at the spectra on the lower right, you see a sample that's just a little too thick. So it's a polystyrene sample by reflection, and you can see the one peak looks like a first derivative peak. So these can have lower signal to noise, and they can be very sensitive to the tilting of the sample, because that will change where the back reflection of the light goes. Now, in the IRAS or RAS experiment, which is reflection absorption, again, you have very minimal sample prep. Shown in the top left there, kind of in the yellow box, is a drop of liquid being put onto a slide that you can analyze, either if the liquid's not strongly absorbing or if you're not looking for something in the liquid, then you could analyze that directly. Or if you need to, you can let it dry down and then analyze it. So you can run liquids using this method. This is really easy, especially if the substrate or the material on which the material you're analyzing is located is reflective, like on a gold slide, which is what's shown in the lower right. That is the laminate I was mentioning. You can see two of them there, one laminate at the top letting you see it, and then the bottom one has been analyzed over its length, and that's sitting on a gold slide. The spectral quality of reflection absorption can be very comparable to transmission, and it's very good for coatings such as paint or something like that on a reflective surface. The negative is that it's very sensitive to the sample thickness. If the sample's too thick, then you get these very strange peaks, or you get nothing at all. It's just totally absorbing. So you have to be careful with that. ATR, as I've said multiple times, is probably the favorite of many people because you don't have to prepare anything on your sample. You just take the crystal, you make sure it's good and aligned, and then you get it in touch with your sample. The spectral quality can be excellent, as you'll see during the presentation. You don't have to worry about the sample thickness because the ATR is only probing, as you can see in that diagram to the upper right, the red line is the infrared beam coming in, and you see it's only probing the very top of that sample. So it's like the outer layer. And it's equally applicable to paper, to rubber, to coatings on surfaces, to just about anything. And that's why it's very commonly used. The negatives is that it's extremely sensitive to the contact with the sample. So if you can't make contact with the sample for whatever reason, you're not going to get any signals. There's also some shifts due to the ATR effect. I won't go into that in detail in this presentation. There are others where I've talked about the ATR effect, shifting the peaks, changing the intensities relative to transmission. But if you have libraries that are prepared with ATR or a correction mechanism, which our software offers, then you can get good matches. And then the other problem can occasionally be residues of the sample on the crystal. So if you're doing a map, you can actually drag part of the sample with you. I once analyzed a sample at a company that makes adhesives, and not only was there residue on the tip just picked up the sample and moved it because it stuck to the tip. That's what it's for. It's an adhesive, so it's stuck. And this made the analysis a little more difficult. But there are ways to get around that and to make sure that everything goes all right with the ATR. Now, I've talked so far about just the sampling, but you also have to consider the spectroscopy. There are a number of things that can go wrong or that are challenges to the IR. They don't go wrong, but there are things that can challenge it. One is if you have an excessive amount of carbon black in your material. This is because the carbon black, the material is usually highly absorbing, and the carbon black is a high scattering material within it, and you get very large artifacts in your collection. Water in the infrared can also be problematic because the spectrum will look just like water, and there are distinctive bands for water. And the other problem there can also be some of the sampling tools that have traditionally been used based on things like salt plates can actually dissolve in the water. And then finally, silicone is a big one. It's one that I'm seeing increasingly in some of the analyses that I've been asked to do. And this is because a lot of the new, more modern epoxies and other adhesives, not epoxies, I'm sorry, but adhesives, are based on silicone materials. A lot of them, like the ones used on styrofoam, they use a silicone adhesive. And silicone has this monstrous quartet of peaks. You see them circled there. Those are the 4 fingers of silicone. And any time I do training, I point that out. If you see those 4 peaks, and you can see where they are, right around 1,000 wave numbers, that is strongly indicative of silicone being there. So it can obscure peaks, and it also shows a very strong, as I said, a lot of times if it's a contamination, you'll see that there. Also, you can't analyze on glass because it doesn't transmit in the infrared. So those are some of the things you need to worry about in the analysis. Now, on the next slide, let's look at the preparation or use of the diamond compression cell. You can see at the top the diamonds. This is one particular type of compression cell. There are actually several. If you look in the center of that image, you see the clear crystal. That's the diamond. And on that, there's a little tiny fiber. That's the sample that was to be analyzed in this case. So the first thing you have to do, and that's what's called a pick pin, that's being used to place the sample onto the diamond. And then you once the sample is there, you clamp it between the windows and then you analyze. It's basically a way, if your sample is a little too thick, of being able to thin that sample so that the analysis will work. One of the key things, if you look in the lower left, is that you need to put a piece of potassium bromide or other IR transmissive sample there. And the reason for that is shown on the right. If you look at ray B2, you see that as it's going through the compression cell, it actually internally reflects. And what will happen in that case is you will see something called fringing. You'll begin to see the effect. It's like a filter. It's an optical filter is what it is, or an infrared filter. And you'll see fringing in the spectrum. In order to prevent that, line B1 passes through the potassium bromide, which is non-absorbing. And then A is passing through the sample. And that's what I will do when I show you the analysis. Now, this is a microscope technique that's been around for many, many, many years in both visible and in infrared. This is where you embed the sample into an epoxy puck. So what you see in the upper left, those are little springs. And if you open the spring up, kind of like you're unrolling it, then you can take your sample, usually something like a multi-layer film or something else that you want to analyze, and you trap it inside the spring. And then you take that spring and you drop it upside down into something that looks like an ice cube tray. Fill that up with the epoxy, allow it to harden, and then you have what you see on the top right. You can see the springs embedded in the epoxy. And then you either shave it down and polish it so that the sample is exposed, because it'll be buried in the epoxy, or it may be buried in the epoxy, or you take this to a microtome and shave off an ultra-thin piece of it that you can analyze on the FTIR microscope. The advantage of this is that, again, you get the transmission capability if you microtome it, and that you get a position that's very well positioned for the use of ATR once it's hardened. The difficulty is just the time it takes to prepare the sample and then polish it. On the lower right, you can see what this looks like. You see the sample embedded. There's a clamp holding it from both sides. So you can see the sample in the middle, the bright white stripe, and on either side of it is the clamp. So that's what it looks like when you're finished. Now, this is a thin film for transmission where I'm microtoming it. And you can see in the top left, that's the microtome. And then in the left center, you can see the blade approaching the sample, cutting off a thin film. And then in the bottom, you see the effect of those thin sections on a KBR disc. I think the first time I ever saw one of these was in the movie Andromeda Strain, when they're cutting a piece off that they've embedded in the epoxy. And you can see them when they shave it off. It's kind of neat. Now we can prepare these samples like that. And you see on the right, the sample embedded or on the film that's been cut by the microtome. And then on the right, you can see a little bit better in polarized light where you can see the individual layers. So now that sample's ready to analyze. A little bit easier way to do this can be the use of a microvise. This is an offering from one of our vendors that works with us, where you clamp the sample, and you can see we're clamping it at an angle. And the reason you do that is because the angle exposes a wider amount of the sample. In other words, if you're trying to see the different layers, if you hold it straight up and down in the clamp, which you can do, then the different layers may be too thin. By tilting at an angle, you can see in the image for the sliced sample that the horizontal layer is now thicker. Each one of those layers is thicker. And that has to do with by tilting at this angle, you're looking at the hypotenuse of a triangle, basically. And it gives you more of the sample to look at. So you can see at the top, my colleague preparing this, slicing it off with a microtome blade, actually, in that case. Need to be careful with that. And then after cutting, you can see the samples sticking up through the jaws of the vise there. And then under the microscope, you can see the layer in the middle of the jaws. Okay, so that's enough about the different preparation tools. There are others. Diffuse reflectance, you basically just stick the sample to a slide and you go to it. That's what I've done with a lot of pharmaceutical tablets. And what I want to do now, though, is step back from that and look at some of the applications that we've recently done and stories from many different fields. The first one is quite a simple little story, looking at particulates in an automotive fluid. Now, this is a shock absorber, and there's something called a piston band within it. There's a fluid inside the shock absorber. And what was done here was that fluid was filtered through a metallic filter. And then we took that filter and placed it directly into the Nicolet RaptIR FTIR Microscope you see pictured there, which has the advantage of being really, really easy to operate. I could show you how to use one of these in probably half an hour, even if you're not a microscopist. But the key is it was done by transmission, just very simply. After the filter dried, we put it on there, and then we used micro ATR to analyze it. You could also use transmission to do it. And you can see at the top the spectrum of the orange particle that you see in the picture there. This is actually a mixture of things. It was not just a single sample. It wasn't just Teflon. And we have software that's specially designed to analyze multi-component materials. That's called OmnicSpecta. And using that software, it basically does a deconvolution of the spectrum to allow you to look at the different components. It's kind of like chromatography done by infrared, where you take it apart and see the individual components. And then you can see at the bottom the 3 different components that were identified. At the bottom is the silane. This is a coating that is applied to the material. And you can see there the 4 peaks. You see 2 of them very prominently, but that is a silane that was on the surface. In the middle is the styrene acrylate copolymer that we see. But at the top is probably the primary constituent of this material, Teflon, that has just rubbed off and floated around inside that liquid during the use of the shock absorber. Okay, so that's one type of sample, just a simple little thing. This is a geology. This is a rock from Mineral Point in the town of Mineral Point, not far from the Madison facility where I work. It is a sample of galena, which is a lead material. And actually, again, just a quick aside, the state of Madison, or the state of Wisconsin, is known as the Badger State. And the reason for the name Badgers came from the miners. They would dig these shallow mines, and then rather than going home at night, they would sleep in the mines. So they got to be called Badgers. And that's where the name came from for the university team and the state. The sample, as you can see, is a thick sample, and the new RaptIR microscope can analyze this no problem. It's a heavy sample, and again, that's no problem. The instrument was designed to analyze this type of sample. There was no preparation done to this. So what you see at the top right there is a visual image of the top of the sample, including this prominent part that's sticking up. There was no polishing or anything done. So that shows you something of the depth of field of our ability to see the sample. And then at the bottom is the map that was collected from this sample, showing a lead compound, probably lead carbonate, which even though the primary constituent of lead may be lead sulfide, you're going to see lead carbonate just from the aging in the environment. And that's what's seen here is lead carbonate. And at the bottom, you can see the different images of different parts of the sample, where the white part is this lead carbonate that we picked up. So a very simple analysis for use on the RaptIR microscope. The next one shows several examples, visual imagery of different samples that are very, very thick, including at the top a book that was analyzed. So if you want to analyze the Book of Kells, I've actually seen the Book of Kells. They don't exactly want to cut a page out of that if you wanted to analyze it. That would not go over real well. But if you want to look at those ancient books or other kinds of materials, you need to be able to analyze the thick sample. This book was 33 millimeters thick. It's actually a book of plastic samples. I drew on it with a felt tip ink pen, and you can see the actual texture in the ink on the sample focused on the RaptIR microscope. At the bottom is an electrochemical cell normally used in the Raman. To the right is a very commonly used accessory for infrared microscopy. That is what's called a heat-cool stage, again from one of our vendors. And there are several around the world that do this. It allows you to trap the sample inside a sampling device that can be purged, can be heated or cooled to liquid nitrogen temperatures, or heated up to as high as 600 degrees. So it's heavily used in like catalysis. A lot of our good friends in China who do catalytic research have these types of elements, these types of sampling tools. And then at the top right, you see a painting which we mounted on the stage of the RaptIR microscope, and then subsequently analyzed the paint on the sample. Now, ink on paper is a fairly common analysis, especially in forensics where you're looking at documents that have been challenged, or in one case we were working with an investigation of a mass murderer in Italy who used a pen, a template to write a stencil template to write his messages to the local police. And when he was arrested, they had the pen, they got the stencil, and they had the notes, and they compared the ink on all three to make a connection between, and he had used a very expensive pen. It was not a cheap pen, so the ink was very unique to it. Now you get an overview of the sample in the visible. If you look at that top image, you'll notice the very large image. That is an overall mosaic of the sample, and it's very difficult to see the mosaic imagery, the mosaic, the lines between the various mosaics. We actually stitch those very nicely, so the sample comes out with one smooth image. This flat fielded image has a very good full view of the sample, and it makes finding the location to do your analysis trivial. Then the bluish colored box is a 15x mosaic that allows you to zoom in on the part of the sample of interest. And then the colored box is the infrared analysis box. So you can see we've done a very large area of that sample, several millimeters in size, using the RaptIR microscope. On the right, just showing the quality of the visual imagery. This is from a business card. And what was neat there was seeing the colors and the high degree of texture in that sample using the infrared material. So it's very sharp, very clear. And this is a huge part of choosing your FTIR microscope. You're going to want to have that visual clue or that visual confirmation that you're looking at the right thing. So that is a look at some of the paper. This is the image I showed on the first screen. On the left, you can again see the quality of the visual imagery. The band that you see in the middle is not a mosaic. That's actually the security strip in that particular currency. And on the right is a Thai bot, where we zoomed in on the head of the emperor and just analyzed that. So you can see the different inks, the different resolution there in the material. So it's very nice imagery with the RaptIR. This is one more. This is where we're looking at a business card, and you can see at the top the size of the image. Notice that it's very large, so we covered a lot of area with that mosaic. You're not just limited to a small area with the RaptIR microscope, so we see the entire business card, or the portion of the business card we want to analyze. And then at the bottom, you see the map that we collected, and then the spectrum of the various points within the map, and you can see the correlation between the visual and the infrared data is outstanding. Okay, on the next one, we're looking at an embedded fiber. This is one of those security fibers very similar to what you saw on the previous slide, embedded in a currency. And in this case, you can see very nicely, this was done by ATR. You can see very nicely that this is a nylon fiber. You see the quartet of peaks around 1500, which are called the amide bands, the amide 1, 2, 3, 4 bands, showing the presence of a polyamide, in this case, the nylon. So again, a very simple analysis there. This was a cool one that was done using the continuum microscope, our predecessor to the RaptIR. In this case, what we did, there were dimples on the surface of the sample. Little, well, just dimples, that's what they were. And the question was, what caused them? Because on a dashboard, you don't want to have the dimples. You want it to be nice and smooth. So we took an analysis looking at this dimple where we actually microtomed it off until we got through to something underneath, and we could see what was underneath visually in the microscope. And then you see at the top the spectrum of the bulk sample, which was simply the polypropylene ethylene material of the dashboard. That's the bulk material. And then we see the spectrum of the inclusion at the bottom. Well, that spectrum matched very nicely to bisphenol A, which is a type of plasticizer. In this case, what happened was the plasticizer is supposed to be homogeneously distributed throughout the blend when the material is being made or formed into the dashboard. This showed that some of the plasticizer had actually aggregated or located into a puddle in the sample or a bubble inside the sample as it was being formed. This caused this defect, and the presence of that bisphenol A stressed the local material, causing this pucker, causing the sample to erupt, if you if you understand, into this dimple. So that was an analysis where we were able to tell what caused this surface defect. Now, this is ATR done on a single fiber. The fiber, as is clear from what I wrote at the top, is actually from my cat. The cat was not harmed. My cat leaves plenty of sample around the house. I don't have to worry about that. But it's just a single fiber, and you can see that the ATR tip contacted the fiber during the analysis. The crosshair you see was used to locate where to do the analysis. Once that was done, we simply touched the sample and we got the spectrum you see in the bottom. You see the extremely high signal to noise, and that is one scan. So the point here is the ease with which the sample could be done on a single point in this case, and then the quality of the spectra that you can extract from ATR. So ATR is a very valuable tool in the analytical lab when using the microscope. It allows you to locate right on this single target. If you had like a single speck from a molding problem, or you had a single fleck inside your soap or something like that, you could analyze that using ATR. Another one that we've done in the past is look at sheets of polymer that are being rolled, and some of the material that's on the roller actually embeds into the sheet and causes fish eyes, little distortions in the polymer matrix or the plastic. Okay, this is now a compression cell. I've mentioned several times we'd be looking at this. And what you see in there is a grain of potassium bromide that has been flattened. Then you can see the laminate sitting next to it, the little curved multi-layer film there, and P1's located right on that laminate. And then down at the bottom are the spectra from some of the layers in the laminate. And you can then analyze it. You take your background on the KBR to get one that has none of that fringing in it. You can see there were several other specks of KBR in there. And also you see some of the, on the surface of the sampling tool, little fibers or stuff that were laying on top of the diamond compression cell, but they do not interfere with our analysis here. To the right is something called the region Q, which comes out of our sample. What was done, the reason I brought that up is because it shows the aperture that was used to collect it. In this case, it was a 50 by 50 aperture, which gave the spectrum you see down at the bottom. We did collect 32 scans, and that got a very good signal to noise. The key to doing transmission is thinness of the sample, and then collecting carefully, maybe multiple scans. There have been times when we've used 300 or 256 scans to collect the data on the sample. Just be patient and you'll get good data out of the transmission. This, as a matter of fact, is a polyester fiber in a compression cell. At the top center, you can see the image of the entire crystal. And again, that was taken, you can see it was a multiple mosaic, but you don't see the mosaic lines on the RaptIR microscope to see the whole thing. And then on the left side of the screen, you can see the zoom in on it, including the high resolution mosaic, the darker gray film or darker gray image in the back, and then the infrared data collected in the transmission cell. And there you can see that this was taken with a 10 by 10 aperture. Again, looking at the region Q 10 by 10 aperture, and with a single scan, we get the spectrum you see in the bottom. There's a little bit of fringing there, but the spectrum is still very, very high signal to noise, even with a single scan at a 10 by 10 aperture. This microscope is hot, so if you need high resolution, it's an excellent choice. And in this case, we were looking for the distribution of the polyester and other materials in that fiber, so we needed to do the high resolution. And putting in the compression cell allowed us to push it down to get a sample thin enough to examine. Now, these are images from the automotive industry looking at a part that was contaminated. That's what you see in the upper right, in a compression cell where the sample's been flattened, and then a spectrum at the bottom of a material, in this case laying on a gold slide, so it's a reflection absorption experiment. And you can see the different colors of material. Now, can't talk too much about what it is because this one's still proprietary, but you can see the quality of the spectrum again and the type of thing that you can do with the two methods. Now, this is a multi-layer film I've mentioned a couple of times. This is done in reflection absorption. This actually comes from a food packaging. In the food packaging industry, you're looking at creating a wrapping material or a packaging material that either permits or does not permit, depending upon the material, the percolation of different gases in the air to get in at the sample. In the US, Americans like their meat to be red. In Europe, they wrap them in a vacuum-tight material. In the US, they wrap them in a material that allows oxygen to permeate, which turns the meat red because it reacts with the myoglobin. And in order to do this, there's a real science behind the food packaging material. Long story to get to the samples, but you can again see in the image on the top left, the two laminates that were on there, one of them just in the visible, the other analyzed with the infrared. In this case, we used a 20 by 20 aperture, and again, just a single scan. You see the spectrum at the bottom. That, when we map it over the entire sample, shows what you see on the top. And then again, the exact same image. The difference in the image on the top and the one on the bottom left is that you can change the percentage of the visible and the percentage of the infrared so that you can kind of see through the infrared to see the sample underneath, to see which parts of the sample the various profile materials line up with. And then on the bottom right is just a little bit higher resolution image of another laminate that was collected, in that case with a 10 by 10 aperture, to get a very high resolution image across the sample. So that's the reflection absorption. This is a technique using a large ATR crystal, which allows you to contact the sample, and then rather than lifting the ATR and moving it to another location, you just analyze the whole field that's in contact. And you could have contacts, depending upon the accessory you use, that can be up to 1 millimeter or even a little bit more, where you then do mapping or imaging across that. In this case, you see a fiber that was analyzed in this way, and you can see the extremely small layers that were visible in the sample. The entire sample there is about 50 microns in size. The advantage of the imaging tool that's used here, this ATR accessory, as I said, is you don't come out of contact with the sample. So I mentioned that case of an adhesive. This would have been a perfect tool to use in that analysis because you would get in contact and stay there. You don't have to worry about contamination because when you lift it up, you're done with the experiment. The next sample where we've analyzed it is a cottonseed, where we were looking for something called gossypol. Cotton seeds in the state of Wisconsin and elsewhere are used as feed for milk cattle. And the concern is that the gossypol is toxic, not to the point usually where it kills the cow, but it can decrease greatly the milk production from the cow. So it's important to know how much of the gossypol is in the sample. So you can see on the top left, there is a visual image of it over the whole seed that's been cut open to expose the interior. And then the inset is a single screen about 500 microns in size. And then the chemical image to the right shows different materials and what those are. I'm going to show on the next slide. I've shown a number of images throughout, and there may be questions of what the colors mean. Well, here's an example where I'm going to define what the colors mean. We've done something called a correlation on this slide. This is again, the cotton seeds. And then what we've done is search the spectra from the different, or correlated is the right phrase, the spectra in the data set or in the overall image or map to different materials. And the first one is cottonseed oil, which of course is what the cottonseed was for, was to give this rich oil. And you see the spectrum there of the oil. If you look at about 1750, the big, tall, sharp peak there is strongly indicative of an ester type of material in the oil. The next one down is cellulose, which is present in almost every natural product of this kind. So you see, if you look in the spectra there to the right, you see the large peak down around 1,000. That's very typical for cellulose, which is a sugar, and that's a sugar peak. And then the next one is the protein. And I meant to stop just a second and explain that when you correlate, the regions of highest correlation in our software will turn red. So as we correlate to the cottonseed oil or the cellulose, the regions where that's present turn bright red. For instance, you can see in the cellulose that in these veins that are inside the cottonseed oil, that's where the cellulose material is located. You see a circle around one of the little spots there that I'm coming to next. Then you can see there is protein in the material. If you look in that green spectrum to the right, around 1600 wave numbers, again, you see the quartet of peaks that are identifying as a polyamide, in this case, a protein. And then finally, the bottom one is the gossypol peak. That's the spectrum of gossypol. So it's actually showing that the gossypol is in those little black things that you saw in the first picture. You see those little pods within the pod. That's the gossypol rich areas. Now, this is a pharmaceutical tablet where we looked at the distribution of caffeine in particular inside the tablet. So you can see two images. The one on the left, again, has the low resolution image of the entire tablet. And then you see the higher resolution box with inside that. And then finally, the infrared data over a very large area. To the right, you can see an image of that sample again, or this is actually a different sample. You can see the white background outside the kind of grayish box. Inside the grayish box, you can see the higher resolution image of the sample. And then you can see the distribution of the caffeine, and the spectrum of the caffeine is at the bottom, showing the distribution throughout the sample. And we can see it's very highly homogeneously distributed. It's not located in one area. This is another pharmaceutical example. This is an aerosol that's been dried onto a gold slide. Won't spend a lot of time here, but you can see the visual image on the gold slide in the background, and then reflection, absorption, and the spectrum collected in the bottom. Now, this is a microplastic sample, and what I want to do is go through this a little bit. This is a microplastic sample. You can see the dots on the right on the large image. This is showing all the different particles that were identified by our visual identification software. So we just click one button and boom, it identifies all the particles for you. Then the infrared microscope jumps to each one and does the analysis very, very quickly and efficiently. It actually calculates the most efficient path through the sample to do it, and it calculates the correct aperture size to use on each point. So very quickly sets up the analysis and then does it all fully automatically. Then the report breaks it down. To the left, you see the three different types of report. At the top is a cumulative report where the software counts up all of the polyethylene, all of the acrylate and methacrylate particles that it saw, identifies how many particles out of the full data set are those. And you can see there the different materials it's as this is a true environmental microplastic sample. This was done by my colleague Suja Sukumaran out in our San Jose lab, using, again, the new RaptIR FTIR microscope, of a sample that was taken from one of the government facilities, just analyzing aerosol samples. So at the top, again, you see the cumulative results, the number of particles of each material identified. The next thing down is showing each individual particle. So in this case, if I could scroll down, you'd see there were like 700 particles in this data set, and you would see the analysis for each one, and that includes the identity, the location in the matrix of samples, and if you click on it, it will highlight just that sample, and then which library was used, and then a visual of the thumbnail of the visual image collected during the analysis. And then further to the right, there's a number of statistical things you can get, such as the circularity, which can identify whether or not that material has been in the environment. If the circularity is very low, it may be a fiber rather than like a plastic particle that's been in the environment for a while and ground down or whatever. So we have all the statistics that you would need to analyze these, from the, as I said, from the location, the image, the identity, which were the main questions, but then also these other statistics about it. And then at the bottom, you can see there is a histogram that can be calculated based on your choices. You see across the top, it says component. The lookup table was the top ranked one. And then the x-axis is the area or size of those particles. And then there's a histogram plotted there of the number of particles with each size, so you can get an idea of the size distribution. If you would pick the circularity, you would get a distribution for the circularity. So whatever you pick, you get that report. And then again, you have the image to the upper right and the spectrum down at the bottom of whichever particle you have selected. So this is a very thorough analysis now in our Omnic Paradigm 2.0 software. So a very, very powerful package to help analyze microparticles, whether you're an expert in the field or not. And this is the FTIR microscopy conclusion slide. The important things in microscopy are to have the visual images and the IR data to combine to give you that story about your samples. Are they rounded? Are they filamentous? Is the surface indented or whatever? If you're looking at a polymer embedded or something embedded in a polymer sheet that's caused a fisheye, you can look at the visual and see the stressing of the material in the vicinity. When I analyzed that bisphenol that was located in the black polymer, it was important to be able to see the actual bubble of material. And really, there's new software tools coming from all over to really drive your productivity. And the spatial resolution, the IR signal noise, combine, and it's not necessary to always collect at the highest spatial resolution to get what you want. That can be a big waste of time. And as you open the aperture, you get a better signal noise. So there's a number of trade-offs here that can be done. And again, with the 3 different microscopes that we offer, you can go whichever way you want. The highly manual IN5, the standalone IN10 in the middle, or the new extremely high performance RaptIR FTIR microscope. Now that wraps it up. I thank you for your attention. If there's any questions, we'll be pausing in a moment to allow you to ask those. But I did want to point out on the slide are a number of resources for further information, including the FTIR Academy, which has a lot more tutorial information on it, and then a lot more information about our products in the FTIR microscopy area, microspectroscopy. And then the emails at the bottom, if you have questions about anything you've heard and you want to email me or in general the spectroscopy webpage, you can do that. But at the bottom is my email if you wish to contact me and ask anything. I thank you very much for your attention, and that concludes the seminar. Thank you.
So thank you for that presentation, Michael. Let's move on to the last part of today's webinar, which is the Q&A session. I can already see that we've got loads of questions coming through, so let's get right into it. So the first question is, do you usually measure through both windows, both windows of the diamond window, or do you remove the window after compression?
On the compression cell, it's usually easiest to go through both windows because the removal of the top window can actually damage the sample, pull it apart, or shift it around. However, I have seen labs where they do remove the top one just in order to improve the signal and noise, because going through the diamond does cause some absorption bands near the middle of the spectrum. But the imagery that I showed and all of the spectra were taken through both windows. I do not take them apart normally myself.
Okay, thank you. And we've got another one here. So what's the smallest size and thickness that FTIR can analyze? And can you share what the best setting is for this type of sample condition?
The RaptIR microscope is good to below 5 microns without using ATR, so it's very high spatial resolution. As far as the thickness goes, that will depend very much upon the sample. We try to keep them down to a few microns, or just a few 10 microns, something like that, if you're doing transmission, because the thicker they are, the more absorption you get, and then the bands flatten out and you get totally absorbing bands, things like that. As far as infrared reflection absorption, that has the problem where you're going through the sample twice, so the problem is somewhat compounded. But still, as I said, I'm looking at layers within that laminate I showed you that were down to below 10 microns thick. And those were done on a laminate that was roughly 15 microns thick. It was actually cut with a razor blade, not a microtome. So it really depends upon the sample. But those are some rough numbers of what we work with.
Okay, lovely. Thank you. And we've got another one here. So what's the advantage? Oh, sorry, no. We'll just put this one in first. So reflection versus ATR. How deep does the FTIR penetrate to give information?
The penetration depth depends upon a lot of parameters. There's an equation that talks about that for ATR. We use a germanium crystal, which gives you a very shallow depth of penetration. So you're probably less than a half a micron deep into the sample. So you're very much looking at surface phenomenon. Like with the currency, you're looking at the ink on the surface. Frequently, you may not even see down below the ink layer, but it just depends upon the penetration. For the reflection absorption and the reflection types of experiments, that depends again upon the material, because the IR beam will go as deep as it can into the sample, which can be several microns. It really, as I said, depends upon the absorptivity of the sample itself. A somewhat difficult question to answer, but with the ATR, you have good control over that.
Okay, thank you. And we've got quite a few more. So we'll go with, what are the advantages of having a tandem microscope and bench opposed to just a standalone microscope if your samples are only for microscopy?
Now, the last part of that question kind of changes the answer. If your samples are only for microscopy, that's why we offer the standalone instrument, the Nicolet IM10. However, with the RaptIR and the attached Nicolet IS50 that you have on the front end, you get a number of other capabilities, including Fourier transform Raman, thermogravimetric analysis, bulk ATR, all of the tools that you would expect out of a research grade spectrometer. Also, in the long run, you will be able to pick up various spectral ranges because the spectrometer can do that and gives us the ability to control some other parameters. But the primary advantage here is the ability to connect to it and get all of those other capabilities. If you don't need them, then that would be looking at the IM10. Really, you just kind of need to sit down with the salespeople and the applications people to look at your app and decide which one is the best route for you to go.
Okay, lovely. Thank you. And we'll go with this one. So regarding microparticles, they're already down to a micron size. So what are the developments required in this?
Well, the primary thing that we developed, as I showed in those last couple of slides, was the use of some technology developed within Thermo Thermo Fisher Scientific is a very broad company, has a lot of expertise. And among that is imaging technology, which was heavily used in the electron microscopy. You may be familiar that FEI, the former FEI, is now part of Thermo. And they developed a lot of 2D and 3D imaging technologies to work with that. So what we did was we imported that technology into the FTIR microscope to give us the most efficient and effective way of detecting the particles. So really that's been the advance. There's a lot of people out there talking about machine learning and a lot of other techniques. The point is we've been doing this for a very long time and have the tools that get in there. The other thing that was developed for this particular tool was the path that the spectrometer takes through the sample is optimized. So in other words, we don't just start in the upper left-hand corner and go linearly through the sample. That would require changing the aperture at each point, or could require that. Instead, what we do is we set one aperture and then we collect all of the particles that use that aperture. So by using the visual tools to optimize the data collection and then optimize the path, we're giving you a very high-speed analysis without the need for an imaging tool or something like a quantum cascade laser. It's just not necessary for this kind of analysis. And furthermore, there's been some details about, well, I better hold on that. That's stuff for the survey that's going out. Next question, please.
Okay. So we probably have time for one more now. So I'll go with this one, and that is, how does the RaptIR scope differ from the Continuum scope? What upgrades does the RaptIR scope offer?
First of all, it's a much more modern microscope. It has a much higher spatial resolution and a much higher quality camera on it. This is a full large scale high resolution so that you get resolution down to below a micron for the visible. And as I said, you're below 5 for the infrared. That's the primary change. All of this is new technology that's being patented currently, so I can't speak to it more than that. The other massive change is the import of the Paradigm software, which is full 64-bit. I recently collected a visual image that was 8 gigabytes in size, something that the previous generations of software could not have handled. The Paradigm software allows me to handle that and then do the data collection and the analysis. So what we're looking at is an entirely new user interface as well as an entirely new technological platform. This is a completely different platform. Even if some of the components look the same, they're not. You can use all of these different, the other thing was that you could use the thick samples. With the Continuum, you were limited on how thick the samples could be that you can mount. As the images showed, you can mount books, you can mount paintings, other things on the RaptIR microscope platform. So those are the big changes, some of the big changes. There's more.
Okay, thank you for that. And I'm afraid that is all we have time for today. But I'd like to thank Michael today for the very informative discussion and presentation. And I'd like to thank everyone joining us online and for your interesting questions. And I hope that you found this a worthwhile session. I can see there are a lot of questions we didn't get to, but please feel free to email me at editor@selectscience.net, and I will follow up your questions with Michael. And remember that you can also download a certificate of attendance in the Related Resources tab to the left of your screen. And also, if you would like to listen to today's webinar or invite a friend to listen, it will be available to watch on demand in a few days. So goodbye, and thank you once again for joining us.
Thank you very much.